Hi everyone, my name is Clara Meister. I'm a PhD student at ETH-Zurich, and today I'll be presenting our work titled On the Probability Quality Paradox in Language Generation. So let's jump right in. We can coarsely break down the task of language generation into two parts: modeling, or creating a scoring function for strings, and decoding, the process of generating strings according to this scoring function. We'll first briefly take a look at modeling. So in short, standard language generation models are probability distributions over natural language strings. In practice, we want these models to assign high probability to realistic text, while assigning lower probability to less realistic options. Now, how do we go about creating these models? Well, typically we optimize the parameters of our model such that it assigns high probability to actual natural language text, or in other words, a corpus. So, how good of a job are today's models actually doing? Performance in terms of metrics like perplexity would suggest very well. In the last few years alone, the NLP community has seen big jumps in model quality with respect to this metric. Yet when we use these same models to generate text, their performance is still subpar in many situations. So if we're doing the modeling portion of the problem of language generation so well, then our issues must be coming from decoding, right? Well, let's take a look at the decoding component of the language generation process. So in the case of locally normalized models, which is the majority of language generators, we generate strings word by word. Now there are many different ways we can go about this process. For example, for the sentence starting with my, when choosing the next word, we could simply choose the most likely word according to our conditional distribution. We'll call these types of rules likelihood maximization based approaches. Some common decoding schemes that fall under this category include greedy search and beam search. Now, a totally different approach would be to sample from our conditional probability distribution. Of course, this means that we will occasionally sample some very low probability words, which may lead to strange text. To avoid this case, we can also truncate the sampling distribution. So instead of sampling from the full set of all possible words, we limit this pool to only the most probable words. Intuitively, we might think that under a well-trained model, the high probability text produced by maximization-based approaches would be superior in quality to stochastically generated text. But it turns out that in practice, there's a strange relationship between the likelihood of text and its perceived quality. Here we can see average human ratings of text as a function of their average per word probability. Note that these texts are generated according to a variety of decoding schemes, both stochastic and maximization-based. The highest scoring text seems to have probability around some inflection point. Now, this phenomenon has been referred to as the probability quality paradox. And in this work, we try to understand this relationship using information theory. So, big picture, natural language is really the primary means for human communication. And we use it in both written and spoken form for anything from mundane tasks to crucial transactions. So in this light, its main purpose is for the transfer of information. So then it seems that naturally, if we wanted to gain a better formal understanding of language, we could turn to information theory, the mathematical study of communication. Now, the use of information theory to study natural language already has a long history, but here we're going to attempt to use it to understand certain behaviors of probabilistic language generators. So first off, how does natural language fit into the information-theoretic paradigm? Well, in our interpretation of the process of communicating via natural language as the transmission of information between people, then human language is a code, or a mapping from meanings to symbols. A natural language string Y is then the avenue through which we communicate information. Now, one important question here is, how is the notion of information formalized in this setting? Well, information theory gives us a formal mathematical definition of information content. Specifically, the Shannon information content of a message Y is its negative log probability. And here the probability distribution that we're speaking of is the true underlying distribution over natural language strings. Now, much research has shown that natural language has developed to optimize for reliable and efficient data communication, subject to cognitive resources. Under this premise, if humans are using language optimally, then they will balance these goals, generally producing natural language strings with a certain information content. Further, on the receiving end of communication, humans would expect similar strings. So what is this optimal amount of information? Well, given a data set of human-generated natural language strings, we can simply estimate it as the average information contained by these strings. Note that this expectation is actually equivalent to the entropy of the distribution over strings. So this brings us to the expected information hypothesis. Now, given our goals of efficiency and robustness in communication, we hypothesize that humans tend to produce strings within a reasonably small range of the expected information content of natural language strings. And how is it possible for us to actually test this theory out? Well, that brings us to our experiments. So while we might not have access to the true distribution P, it happens to be exactly the thing that our language generator Q is approximating. And it's not a perfect approximation, but it should be quite good given that these models are performing so well on metrics such as perplexity. So this means that we can use Q to approximate the information content of a string simply by taking its negative log probability under our model. So now we can continue with our original question. What does the information content of a string tell us about how human-like it might be? In our experimental setup, we look at the task of story generation. So that is, given a prompt, we use a model fine-tuned on a story generation dataset to provide continuations of that prompt. We use a number of different decoding schemes, including stochastic and maximization-based methods, and we also look at the probability of the reference stories for our prompts under our model. In order to score natural language strings, we use human annotators to rate strings according to a number of different criteria, and we then average these scores to get an aggregate quality score. So let's take a look back at our probability quality trade-off graph from earlier. Given our definition of information content, we can now look at our graph differently. That is, as a trade-off between information content and quality. And in this slide, it indeed appears that high-quality strings are within a certain information content. Further, if we separate our strings into different groups, we notice a trend. Both the reference strings and the top model-generated strings have information content distributed closely around the average information content, that is the entropy, of the model. And finally, we can look at the scores of natural language strings with information content within a small epsilon of model entropy. And here we set epsilon equal to the standard deviation of the log probability of samples from our model. We can again see that there's a stark contrast in the quality distribution of strings with information content close to our entropy, as opposed to those outside of this range. So here we have a few takeaways here, but I think I'm out of time. So with that, thank you for listening, and here's a link to our paper if you'd like to see more about our explanations and experiments.